Imagine millions of gallons of chaotic water surging down a gorge. We build dams to neatly channel that pressure into perfectly stable reservoirs. In data warehousing, a materialized view performs an identical function. It pre-computes complex queries and stores the results, granting downstream consumers instant access without the latency of calculating massive datasets on the fly. Prioritizing instant read access creates a specific trade-off. To keep those pre-computed dashboards accurate, the underlying data must be continually updated, an operation that requires consistent cloud compute. When the processing engine only evaluates the newest rows of data, an incremental update, the computational cost stays low. However, if the engine evaluates the entire historical dataset from scratch, you incur the heavy compute penalty of a full refresh. In many traditional cloud data warehouses, these maintenance routines run in the background. The exact mechanics are hidden, leaving engineers disconnected from the physical timing of the system's execution. Optimizing read latency for end users creates a systemic risk if you cannot see or control exactly how and when the underlying compute is consumed. Engineers often assume that defining a materialized view is enough to ensure efficient background updates. They expect the engine to manage the maintenance incrementally by default. In reality, specific query logic, like nested joins or advanced aggregations, often prevents the system from processing incrementally, forcing an expensive full table scan without alerting the user. When an unoptimized view is deployed, a single node processing a full table scan triggers a spike on the compute cost meter. Because this default behavior is opaque, data teams end up reactively debugging massive cloud bills after the compute has been consumed. To address this, Azure Databricks made two features generally available on May 27, 2026, Materialized View Refresh Policies and the EXPLAIN CREATE command. These tools isolate the validation of mathematical logic from the physical timing of execution, changing view maintenance from a reactive process into a deterministic engineering pipeline. Historically, engineers had to write query logic and deploy a view into production, simply to see if the engine could handle it incrementally. This trial and error cycle wastes computational resources, as you burn budget to test if a drafted logic structure is even viable. The EXPLAIN CREATE Materialized View statement removes this inefficiency. It is available in Databricks SQL and Databricks Runtime 17.3 and above. This command functions as a static analyzer. It does not trigger a data refresh or execute the query. Instead, it evaluates the underlying query based on its mathematical structure, confirming the engine's capabilities without moving any data. Validating the logic before touching base tables changes the cost profile of developing a data pipeline. An engineer uses this static analyzer at the start of the development sequence, immediately after drafting code but before committing to the build. The parser block receives the command, isolates the query text, and evaluates the logic without connecting to the data tables below. It generates a binary output confirming if the query is incremental. Because there is no data extraction, this validation consumes almost zero compute resources. Identifying a full table scan through upstream validation ensures that a view will not generate unexpected costs once it hits production. Validating the logic secures the how of the update, but it does not dictate the when. Materialized view refresh policies provide the secondary mechanism needed to control the timing of that work. A refresh policy acts like a mechanical gate. As data builds, the gate remains closed. Incremental refreshes allow a measured portion through, cleanly updating the view. To set a new baseline, a full refresh opens the gate entirely for a coordinated, massive data flush. Separating logical validation from execution timing gives engineers explicit control over how their cloud infrastructure is utilized. Scheduling a refresh sequences your data flow while directly optimizing raw compute costs. This exact coordination prevents refresh collisions, where multiple massive updates might otherwise attempt to run during peak usage. Beyond cost control, these policies provide predictable workload schedules for the entire platform. Predictable schedules allow architects to right-size their serverless or provisioned clusters with precision, rather than over-provisioning for unexpected spikes. Granular orchestration turns cloud resources into budgeted line items rather than reactive expenses. These tools establish a new workflow for data engineers, moving from definition to deployment with high confidence. Step 1 is writing the initial query logic. Step 2 uses the static analyzer to confirm mechanical viability before execution. Step 3 applies the refresh policy to dictate the physical execution rules. Following this sequence ensures that a production environment remains free of unplanned full table scans. Materialized view management has shifted from a process of trial and error toward a system of upfront validation. This methodology is accessible through Databricks Runtime 17.3 and Databricks SQL. Mastering these policies transforms unpredictable data flows into synchronized industrial mechanisms. This approach balances downstream read latency with upstream compute predictability. Using these tools ensures that data movement is always paired with deliberate, scheduled control over the compute resources powering it.